Okay, so I did turn the camera on. No one was absent today, but we had several people doing makeup tests, so they might need to watch the video, so I am recording these notes. First of all, there's a typo. I know, it's hard to believe. It's hard to believe it, and this is, sorry, I had a typo. Okay, chapter 10 is on comparing two populations. And the difference is going to be, hey, in chapter 8, we did all confidence intervals. In chapter 9, we did all hypothesis testing. In chapter 10, you're going to do it all in one chapter. Okay, so 10.1 is going to be all about proportions. You're going to do confidence intervals and hypothesis testing with P's and P hats and Z's. And then 10.2 is going to be all about mu's. You're going to do confidence intervals. You're going to do hypothesis testing with T's, okay? So you can see a lot of the vocab looks pretty familiar because you know about Z tests and T tests and confidence intervals, but everything now is two samples. The one new thing I would point out is this thing, the pooled sample. And we probably won't get into that until tomorrow, but that's going to be something that's very unique that you use only in one particular situation, okay? Calculator skills, I list them here. These are all the new things we need to learn how to do, but they're all going to be like the same thing. You're just going to be choosing different options in your list. So instead of having one proportion, you're going to have two. Yeah. All right. So we ready? Yeah. Welcome to quarter 4. Marking period 4 for us starts today. Yeah. When are the you just took them and I still have makeup today. Good Lord, what do you want from me? You know what? The problem is you've gotten spoiled because I've been really good this year. I've been like lightning this year and I spoiled you.
Yeah, now we just expect it.
I know. No, seriously, when there are makeups, I don't rush as much because like I can't give them back anyways. And I gave a 2-day test in Algebra 2 and they are all done.
Yeah.
And your multiple choice is even done.
Yeah.
So I've made a series done already.
I'm good.
I said I am on fuego. All right, so here we go. 10.1, we're comparing two proportions. So in chapters 8 and 9, we discussed inference regarding a single population. We will now consider inferential methods for comparing two populations, beginning with population proportions. Okay, so you remember those conditions you had to go through? Okay, you now have to go through the same conditions twice. You got to do it for population 1 and 2. So seriously, it's gonna just feel so, it's dull. Okay. So here we go. Population 1. So at school number 1, 70% of students did their homework. Great. School number 2, 50% did their homework. What's going on with school number 2? We don't know. At each school, a counselor takes a simple random sample with details shown below. Okay, so for population number 1, this is school number 1. And notice everything now has a subscript to represent which population you're in. Okay, so it was stated that it was a random sample. Independent, every student is independent of one another, but I can quantify it by checking my 10% condition. So 10 times my n size, in this case was 100. So that gives me 1,000. Have I sampled less than 10% of my population? Well, if my entire population is a school with more than 2,000 students, I'm good. Sample is less than 10% of population. Got it. Normal, n times p. My n size was 100 here, and my p is 70%. So that's going to give me a 70 versus 30. And that's greater than 10 for both. And remember, it could be greater than 5 depending on some different textbooks and different websites. All right, greater than 10 we can assume the distribution is approximately normal. And then we do it again for population number 2. I know, it stinks, doesn't it? Now, if you want to shorten your work and if you want to combine them, you're welcome to do that as long as every time you do something, you address both populations, both distributions. So if you want to start by saying a random sample was stated for both populations, you can do that, okay? But just make sure, don't just say random sample was stated. Okay, if you want to continue to say for both populations, that's all right. Just make sure you address them both, okay? So I'm going to now do my independent condition. So 10 times this n size is 200. And is that less than my population? Yes. Okay. So sample is less than 10% of the population. Again, if you want to do one statement there, show the math for both. But then if you want to say, we have sampled less than 10% of each population, I'm okay with that. Just make sure you address both populations. So my normal condition, n times p, well, that's 100, which means the other one's going to also be 100. Greater than 10. So here, we can assume distribution is approximately normal for both populations. There we go. Now we can do that in like one sentence. Okay, just make sure you're showing the work by explaining for both. It's just time consuming, right? I know. Now, back in, what was that? Was that chapter 7? We did sampling distributions, I think, where we learned that if we took samples repeatedly, that it would create this approximate sampling distribution. And this says if the counselors repeated this 1,000 times, the approximate sampling distributions might look like the following. All right, so this one for the first population, you can see it's centered at 70%. Not surprised, okay? The other one is centered at 50, not surprising. You can see those approximately normal distributions. But what we want to do is if we want to compare the two populations, what we often do for a comparison is we set up a subtraction, a difference between the two. So it says consider the sampling distribution of p hat 1 minus p hat 2. Now, just intuition seems to make sense that this is now going to be centered at 20, the 70% minus the 50%, okay? It's the standard deviation again that, first of all, you don't even know what the standard deviations were, but even if I told you what they were, you don't have a rule for the subtraction between the two. I can tell you that the standard deviation of this is about 0.058. The question is, where did it come from? Oh, we got to figure out our formula. Okay, so back to the chapter on random variables, okay? So if we define P1 minus P2 as the difference, okay, so population 1 could be considered a random variable. Every time we take a sample, we could get something different. Population 2 could be a random variable. Every time we take a sample, the proportion could come in slightly different. So the rule for random variables was, if you want the mean for the difference, you could take the mean for the first one minus the mean for the second one. And in our example, what that pretty much represents is taking that 70% minus the 20% really does give us, or excuse me, minus 50% gives us the 20%, which I said, based on common sense and intuition, that one felt right to us. But it really does follow the rule for random variables. Oh, side note, by the way, does it have to be P1 minus P2?
No.
It does not. Okay, generally speaking, I think I've mentioned this, we often will set up the subtraction to make sure it comes out to be positive, okay? But you could define it in reverse if you wanted to. All right, so here we go. You remember the rule about standard deviations with random variables? Okay, so we have to start with the variance for the difference, which means we have to use the variance for P1, and we have to use the variance for P2. And do you remember the other part of this rule? You always add, even if you're subtracting the random variables. Remember I said I always have to kind of look at the Pythagorean theorem. Okay, so if I want the standard deviation for a single proportion, where's my formula page? Here it is. I got it. Bless you. If I need the standard deviation for a single, right there, for a single population, right there. But I have to put in the subscript. So this one, the standard deviation for the first population would be P1 times 1 minus P1 divided by the n size, and you have to mark that with a 1 also, and then that would have been under a square root. That's the standard deviation for P1. But I need the variance, so I would have to take that whole thing and, yeah, so when I square that, it's going to cancel out that square root. And then I put a plus sign, and now I have to do it for the second population. So P2 times 1 minus P sub 2 divided by n sub 2, that would be under a giant square root, but that would get squared because of the variance. And now those would cancel out. You're like, oh, cool, I don't have to have any square roots anymore.
Yeah, you did.
Except you do. Because at this point, that is still equal to sigma squared for the difference. So for me to get back to sigma for the difference, you're going to have these two fractions, which are connected with addition. So now when I take the square root, it goes over the whole thing. And you can't break those apart because square roots and addition don't work like that. That is literally your formula. And if you go back to the formula page, ta-da, there it is. There it is. And that would be the difference. It would have been the same thing even if you had defined it as P2 minus P1. Okay, it wouldn't matter because you add those. Okay. But of course, we also talked about in the last couple units that sometimes we don't even know what P is. Sometimes all we have is a P hat. So you know what we do? We sometimes put P hat in there. And then we just call it standard error instead of standard deviation. Oh, look, that's on the formula page too. They're there. You just have to know when to use them. And the rule is if you know P, we use it generally. And if not, then we'll go to P hat. Okay, it actually used to be the old formula page. They didn't even give you this. They just gave you this, and then it was your job to just know that sometimes you have to use P hat instead. I kind of liked that better, but whatever. Oh, then they had this other thing here. Okay, remember that thing I talked about on the front page, the pooled? Some people call it the combined proportion, and that's why that one is called P sub C for combined. We'll talk about that tomorrow. Okay, we'll talk about that tomorrow. All right, so what we're going to now do, we're going to do a 2 proportion Z interval. 2 proportion Z interval. Okay, and again, where this whole crazy thing comes from, you're not going to see that formula on your formula page. You're going to see that. But then if you went back to the front page, you got that same generic one that you had before. Statistic plus or minus critical value multiplied by your standard error. You have to know how to build that yourself, okay? This assumes conditions have been met for each sample. All right, ready? Okay, so this example that I have here, I forget why I looked it up one year, but I think I probably looked up because it said it was in Michigan. I looked up where it was, and it was actually in Ypsilanti, so not too far from where we live. Okay, and so this study was actually kind of cool because the study lasted like 20 or 30 years. They identified their individuals when they were children, when they were 3 or 4 years old, and what they did was they took a random sample of kids who their parents enrolled them in preschool, and then they took a random sample of 3 and 4 year olds whose parents did not enroll them in preschool. Now, what happened was they were all from just poor, non-wealthy families. Okay, and if you're familiar with Ypsilanti, there's a lot of underprivileged, families in Ypsilanti. And basically, the whole goal of this was to find out, does that early education propel someone on a trajectory that would make them less likely to have to rely on government assistance in the long run? So they took these 3 and 4 year olds and they followed them for like 20 years until they became adults. And then they kept track of, did they need social services as adults? And mainly it meant welfare. So they were trying to find out, is that early education a reason that would, if someone did not have that now they're more likely to need social services. Okay. So like I said, I just thought it was actually a really cool study because I thought the whole idea of the education was interesting, plus the fact that it was so local. All right. So a control group of 65 children represents population one, poor children who did not go to preschool. I'm going to write that down before I forget that. Population number one, this is no preschool. All right, so how many do I have in population one? 65. So that's my n size. That would be n sub 1. So n sub 1 is 65. All right, and then population number 2 must be the children who went to preschool. And my n size for population 2 is 58. Now, I think I've mentioned to you, I love when they do this, okay? If the n sizes are different, there is no way you're doing a matched pairs, okay? How can you match them up if they don't even line up, okay? What you have to be careful as you go through this is, what if the n sizes were the same? You would have to know that this is still not going to be a matched pair, because at no time are they saying that I'm going to take child A from over here and line them up exactly. I'm just saying I want to find out what happens to all of these. And I want to find out what happens to all of these. You really have to be careful. Once you have equivalent n sizes, you have to really stop and say, am I lining them up 1 to 1? And then I can call it a matched pairs and then create just one new data set, or am I keeping them separate? Okay, so in this case, even if we had two n sizes of 65, I would say it's still not matched pairs because I'm not lining these kids up 1 to 1. Okay. All right, so here we go. We got to do conditions for all of these. Okay, so both samples were random as indicated. So I kind of stretch it across, but I make sure I address both of them. All right, let's do my 10% condition. 10 times my n size here. And I'll do 10 times my n size here. All right, and in both cases, is that less than my population? Yeah, I think so. In both populations, our samples were less than 10%. All right, normal condition. Now, when you end up doing your n times p and your n times 1 minus p, or in this case, it's got to be a p hat, I would come over here and I would figure out what p hat would come out to be for population 1. Out of those 65, now you have to think about what, in terms of probability, we're counting successes. However, in this case, who we're counting is how many kids needed welfare, how many families needed welfare. Okay, that doesn't exactly sound successful to some of us, but because that's what we're counting here. All right, so in this case, how many of these adults years later needed welfare or social services if they did not have preschool? All right, that's, yep, 53 of the control sample needed social services. Don't turn that into a decimal yet. Just leave it alone right now. And then I'm going to come over here and do the same thing. P hat sub 2 is going to be out of the 58, 36. And those, by the way, those are called your X values. That's the number of successes. You're going to need that when you get to the calculator, okay? These would be considered your X values. It's the number of successes. All right, so if I want to set up my normal conditions, I need to do N times P hat. So I'm going to do N, which is 65, times P hat. Now, do you see why I say don't change it to a decimal just yet? Because it just cancels. So in other words, there were 53 successes versus 12 failures, which are, of course, greater than 10. And then over here, I'll say N, 58, times P hat, 36 out of 58. Well, that's going to be 36 versus 22, greater than 10. All values are greater than 10. We can assume both distributions are approximately normal. Now, if you want to change these into decimals, you can. I have 53 over 65 comes out to be about 82%. And I have the other one comes out to be about 62%. Now, on the homework, I tried to shorten the homework. In fact, as when you look at the assignment, 11 and 19 used to be on my list, and I took them off. I'm like, you know what? They're redundant. They're repetitive. If you just want extra practice, they're great questions. But otherwise, I really tried to shorten this a lot. However you want to abbreviate your conditions, I don't care. Okay, as long as you don't do it on the test and you don't do it on May 5th. Okay, just make sure you understand what to write for the conditions. All right. So now we're constructing a 95% confidence interval, a 2 proportion Z interval. Now, if you called it a 2 sample Z interval, you're going to be fine. Okay, you do have 2 samples, but the biggest thing is I like to name it what it's called in the calculator so I remember what to look for. Okay, now if you want to put in the calculator first, you can. I'm not going to because it says set it up by hand and we'll confirm it with the calculator. All right, so the format is your statistic. Well, I actually have 2 statistics. I have an 82 and a 62. But what I'm trying to calculate is the difference between those. So my statistic turns into 82% minus 62%. Now, if you just want to write that as 20% because you did the subtraction in your head, fine. I don't care. Okay. But then it's plus or minus your critical value. So your Z star, do you remember what Z star is for a 95%? Nice. And then we have that giant square root. Okay. So what you're going to do is you're going to set up one of those formulas for standard error off of the 82%. So it's going to be 82 versus 18 divided by that n size, which is 65, plus, then you're going to work off the 62%, which would be versus 38, divided by that n size, and that whole thing is under a very large square root. Now, The good news is that's very easy to type in your calculator. You don't need any like parentheses or anything. If you open up a square root, you should be able to type it right in order. 0.82 times 0.18 divided by 65 plus 0.62 times 0.38 divided by 58. You don't need any parentheses or anything. Your order of operations are all going to be good. So that would be about 0.08, but I'm not done with that yet because I still need to multiply by 1.96. So this whole thing together, which is still called your margin of error, that whole thing is worth about 16%. So we have 20% plus or minus 16%. So our interval is about 4% up to about 36%. And the concluding statement. We can be 95% confident that that says believe it or not, that the interval 4% to 36% contains the true, now in context, detail. What are we trying to capture? The true proportion of the difference. The true proportion of the difference between adults who needed social services based on whether or not they attended preschool as children. Again, on the homework, if you want to shorten it and just say, we could be 95% confident, dot, dot, dot. Okay, that's fine. Don't do it on my test. Don't do it on May 5th. And don't just say, it contains the true proportion of the difference. The difference of what? Okay, we're trying to measure, because you got to think about what this researcher was trying to figure out. This researcher was trying to decide, does going to preschool help reduce the number of adults who would have to claim welfare? What do you think? All right. Do you notice that that interval does not contain 0? If there was no difference between going to preschool or not going to preschool, when we subtract, we might not expect them to be exactly equal, but if there's no difference, we might expect, a 50 and a 40 or something. We would expect the subtraction not to be that far apart. But what we have established with this margin of error and this is that we've established that 20% span is larger than what we're just going to get from random chance, okay? This interval does not contain 0, so we would have reason to say there is a difference. In fact is, because the interval came back entirely positive, I have reason to believe that people who don't go to preschool very likely may need social services later on more often than the ones who do go to preschool. So this becomes an argument for offering preschool to more people, okay? When I grew up, and granted, I'm way older than you guys, we all know that, but Dilla Birdie and I are only 4 years apart. And then we have a brother in between. They did not go to preschool because even back then in the 70s, preschool was not a regular thing. Now, by the time I got to be 4 years old, our district started offering preschool to 4-year-olds. So I went to preschool. They did not. Okay. So it's stuff like this that people will start making decisions saying, okay, maybe we should make this a state mandate that everyone goes to preschool. They might say it costs a little bit of money when the kids are younger, because now we have to pay teachers and stuff like that. But the point is, in the long run, maybe these people will now be more self-sufficient and won't have to rely on the government as much. okay? So based on your interval, is there statistical evidence to support the fact that there is a difference? Yes. The interval does not contain 0. And that would mean that there was no difference. 0 means no difference. All right, you ready to learn? Did you join your calculator yet?
I did it on the last one.
Okay, so I'm on my Inspire first. Now, I have told you guys, I've had students in the past that they tell me, I like to do my calculator first because then I know what the answer is supposed to be. You know, it might be a little round off error, but you at least have an idea. I'm fine with that. Okay, as long as you're showing all your steps eventually. All right, so again, the nice thing on the Inspire is you have 2 separate menus. You have your interval versus your statistical testing. All right, confidence interval. There it is, the 2 proportion Z interval, option 6. Okay. X1. So in population 1, there were 53 people who needed social services out of 65. In population 2, there were 36 out of 58. We did do a 95%. This is the other reason sometimes my students have said they like to do this first. Not only is it a way to check your answer, it will give you the p-hats. It's really dumb, but it saves you that one step. Like I gave you the 82 and the 62. If I hadn't given you those, what would you have needed to do? You would have had to like type it in. If you do this first, you're like, oh yeah, it's 62 and 82. Okay, whatever. So it gives you, now you'll notice here, it says upper, it's like, where's the lower? This list has gotten so long. Yeah, you're going to arrow up. Okay, there's enough of a list there that now you have to arrow up to see everything, okay? If you are on an 84, of course, your stuff is all buried, so we have to find our 2 proportion Z interval. There it is. Same thing. We have 53 out of 65. We have 36 out of 58. And there it is. So use that, either do it at the very beginning so you get those percentages right away, or do it at the very end as a check, whatever. But just make sure you know how to do that. But make sure you're actually showing your work. All right. I'm going to start the next page, but we're not going to get into it because this is where the pooled stuff begins. All right. So what if we were doing a statistical test here? Now, we already know that we would have reason to believe that going to preschool can reduce the need for social services. We know that from our confidence interval. Now, for a statistical test, the null hypothesis should say that there is no difference between the 2 populations. So your null hypothesis will very often look something like this. And remember, no hats on these. So you would start by saying that I don't think there's a difference. Okay, if you're in the group that didn't go to preschool, or if you're in the group that did go to preschool, I think your chance of needing social services is the same no matter what. But you also need to understand that that could be rewritten as P1 minus P2 equals 0, which is kind of what we were just doing in the confidence interval. That's just simple subtraction there. Now you also know that your alternative hypothesis has to use a not equal to. So first of all, you could say there is a difference. They're not the same. You could have said P1 is greater than P2. You could have said P1 is less than P2. And changing all of these by subtracting P sub 2. We could then switch them all into statements that compare to 0, which is super common, okay? Now, without going through all the stuff, let's just quickly kind of go through how this would go in our calculators. I'm back to my 84. This would now be a 2 proportion Z test. So option 6 on the 84. All right, now you'll notice on the 84, it kind of even populates the numbers. It knows I just typed those in. They're like, do you want these again? I'm like, yeah, cool, thanks. Okay, now, what were we testing though on this? We were pretty sure that, population 1 was going to come in higher than population 2. That's why we would have subtracted. All right, so when I go to this, I would want population 1 greater than population 2. All right, and you'll notice it would come in with a Z-score of 2.41. So think about if you drew the picture and you would be doing what's the probability that Z is greater than 2.41, and the p-value, the answer is 0.008. Would you have reason to reject the null hypothesis? Yeah. Okay. So you would now be rejecting this in favor of this, and you could now conclude that we have sufficient evidence to say that the proportion of people who need social services without preschool is greater than those with. Now, the other thing I want to point out, okay, there's your 82%, there's your 62%. You see how there's another p hat in the list? That's that pooled or combined thing that I need to talk about tomorrow, okay? So there's going to be 3 p hats here. There's a p hat 1, p hat 2, and a p hat sub c. And we'll talk more about that tomorrow, but I just want you to see that it's in the list. Inspires, did you find yours? So menu, statistics, stat tests, option 6. Yours does not repopulate like the 84 does. That's sad. That was sad. Okay, so what do we, I don't even remember what the numbers were. 53 out of 65 and 36 out of 58. We're doing greater than. And you have the same thing, p hat 1, p hat 2, and there's your p hat sub c. Okay, so that's what we're going to learn how to do tomorrow. So how do you know how much of the homework you can accomplish? Because I don't have it broken down. You can do anything with a confidence interval. If it actually wants you to conduct a test, don't do it. Okay, because you need to know about that pool thing. Okay. Usually not. Usually not.
But if one of them didn't work, you can get it out.
Then you sometimes get into the, let's say one of them, the normal condition, you got a 2. But the other one, you're okay. You might say, one population is a little bit, it's a little bit small for the normal condition. I will proceed with caution. Yeah.
I don't know. It could be, but it also couldn't be. Like,
Now, you remember what I told you?